Hello, everyone, and welcome back to AI for 2021. We are so excited to have Diego Oppenheimer and Trey Morrow here giving a talk entitled Accelerating Public Health Research, Why Healthcare Needs MLOps. For both speakers, please come and say hello to the audience. Welcome to the virtual stage.
Hey, everybody. Happy to be here. Really looking forward to the chat today. So first of all, a very quick introduction. So my name is Diego Oppenheimer, and I'm the co-founder of Algorithmia, recently acquired by DataRobot, and I've specialized in the MLOps space for the better part of this last decade.
Hi, I'm Trey Morrow. I've been with Algorithmia and DataRobot since February this year. I have about 20 years of experience in data analytics and data science across different verticals, and just glad to be here.
Great. So let's get started here. So if you can go to the next slide, Trey. So one of the important things to think about is that vaccines have actually been one of the greatest success stories in public health history. There's been probably a dozen different vaccines that have really changed the world of humanity. And one of the exciting things of what's happening here is that actually machine learning has actually become a very integral part of how vaccines get researched, developed, and actually deployed to the world. So very exciting time. And we're going to talk about some of the challenges of how do we actually use machine learning in the vaccine research space, and what are the challenges that agree with that. So when we look at actually some of the challenges of moving through the funnel, so if you think about it, vaccine research goes through trying to understand the different virtual compounds, being able to quickly screen them. There's a massive amount of investment. It takes billions of dollars to actually get a vaccine from its research phase all the way deployed to humans in a safe and manner. You're all pretty familiar of what's happened over the last 2 years and how we've accelerated this kind of research a lot. And a big part of it is the actually ability that we've had to apply machine learning to the space. So one of the interesting components about this, it's very limited by hardware. This requires a lot of imagery, a lot of models running against it. The scale of the computation it's exponential, and managing the infrastructure to be able to actually run models against these compounds is extremely challenging. So this is a core part of what MLOps does in this space. So when we look at the traditional challenges of machine learning operations and management, there's a couple of components that need to be actually solved for. So one is what we call stuck in the lab. And this means, how do we actually get models that are trained by data scientists in a research environment, in a development environment, into production and running? How do we actually make that across that chasm so that we can actually say, hey, we can actually run all these models against the real data, the production data, and get the result? In a lot of cases, it requires coordination between DevOps teams and research and data science teams, and they look at the world in slightly different ways. So how do we get these teams together and thinking, hey, we need to work within security paradigms, within governance paradigms, with data access paradigms? There's a wide variety of technologies that are being used for this. So everything from new types of neural nets to different kinds of frameworks, to different kinds of languages. And scientists, especially research scientists, are usually using the technology that they're most comfortable with. How do we translate that technology stack into a production-ready stack inside an organization? Obviously, there's a lot of cases where machine learning has failed to produce results, and this actually drives to a little bit of nervousness in terms of making these investments. They're expensive investments in people, process, technology. How do we actually get the stakeholders to buy in? A lot of, we're in the infancy of machine learning, and there's been a lot of one-offs. So we have a model, we deploy it, It's a one-off thing. We don't have a repeatability. This causes a massive amount of hidden technical debt inside the stack. And it's actually one of the things that, most people ignore. How are we going to maintain these systems over time without this causing us big delays on this? And then finally, what we talk about is this is all part of this inefficient machine learning lifecycle. So if we start looking at getting stuck in the lab, how the teams are disconnected, how we have multiple technologies, how we have sometimes problems with stakeholder buy-in, and finally, accumulation of technical debt. At the end of the day, this is actually going against an efficient machine learning lifecycle, which really should be focused on high repeatability, high iteration, and quickly being able to get to production. So what does this actually all look like? 85% of projects fail to scale past proof of concept. And if we're actually looking and saying, okay, we're actually going to be using machine learning for vaccine research, a failure rate this high is really going against, like the goodness of humanity. And so how do we actually think about reducing this failure rate, actually taking care of some of these challenges, which can actually be, with different technologies in the MLOps space can be addressed? How do we actually reduce this failure? And more importantly, speed matters. If we go look at what's happened over the last 2 years, the ability to actually get a vaccine out and delivered into the hands of people has been saving lives. And so it's important that we can actually get quickly into production, but without risking, not taking care of security, not taking care of safety, and making sure that we're doing it in the right way. So you're talking about Merck. So Merck has used Algorithmia to speed up analysis of the novel viruses in development of vaccine. It's actually allowed their researchers to use an integrated development environment of choice so they can train on any platform and bring their custom models and deploy them directly into a serving and deployment platform that just works. They have a best-in-class technology stack that actually is going to help them screen virtual compounds quickly and cost-effectively, scaling over hundreds of GPUs instantly so that they can actually process through these vaccine requirements. And having applied a stringent MLOps process has given these teams the ability to publish models with low latency and highly efficient compute resources, making that life cycle and that efficient machine learning life cycle much quicker to go through this vaccine process. So what are the actual results? Well, increased capability up to being able to process over 12,000 images an hour. And that's a 3 times increase through the previously what they were doing. It's an automated and streamlined machine learning infrastructure and operations. I can just deploy models, get APIs, run it against data set. Security, governance is all taken care of for me. And it actually simplifies the workflow of high performance computing and allows researchers to focus on the R&D efforts to build vaccines. So we'll be sharing the deck later and a link, and you can actually see my colleague Cam over from Merck talking about exactly how they've implemented this, and we highly recommend going seeing that other presentation. So with that said, I'm going to pass this on to my colleague here, Trey, who's actually going to show this live action.
All righty, thanks, Diego. So AI-powered technology has been assisting practitioners to better diagnose their patients as well. This makes them more readily able to prescribe the right treatments and monitor the evolution of different diseases. At the same time, AI needs to be hosted in a secure, scalable, and HIPAA-compliant platform. Some uses for this would be like low red blood cell diagnostics for like anemias, like hemolytic or sickle cell anemia, G6PD deficiency, which is a enzyme that protects red blood cells from being destroyed during metabolism. And then also something like for patient blood loss during surgery. So basically when they need to transplant or transfuse blood due to blood loss, you can more readily identify what types of cells are deficient. And so some example lab tests that I'm going to simulate here using this technology would be like a blood smear, complete blood count, basically identifying red blood cells, white blood cells, platelets, and etc. You can train this to be even more detailed, but in this case, we're using a data source, or we're training this model to identify these 3 different types of blood cells. You can also do things like differential counts, which you can identify and count the number of white blood cells that can be indicative of autoimmune diseases. And then to do this, we're actually going to use a model called YOLO. This version 5 means you only look once. This is actually referenced in an NIH article that we'll send out the link at the end of the presentation, where this is actually compared to like a convolutional neural network model. This is actually shown to be 3 times faster than that. So I'm going to go into the next slide here. So here you've got kind of a process flow where I've actually trained a model outside of the platform. In this case, I'm using Colab and Jupyter. I've done it on both. Training a PyTorch model with the YOLO framework, and then using RoboFlow to build the training data set. So once we got our model trained, we upload it from our Jupyter notebook or Colab, put it in a hosted data collection on the Algorithmia platform. Additionally, we put our input files in a hosted data collection, and then also the output files. After we do the inference with the labels, it'll be shown on there. So once we got the model and the input files on there, we run the inference on specific file on a GPU node, and then wrap that in a secure API. So it's all encrypted and it's all traceable, auditable, HIPAA compliant. So from there, we save the output file into a repository, which can then be consumed by, excuse me, another algorithm, or you can place it in like a patient chart. So with that, I'm going to get into the demo, and I'll switch gears here real quick and go into, so this is our landing page. And so we organize everything into a model catalog. And so I'm going to drill down into that here real quick. And so we've organized these into 4 different categories. They're searchable. We have text analysis, computer vision, machine learning, utilities. So we've got thousands of different models in here. So what I'm going to do is I'm actually going to search for blood cell. And this searches our model catalog. And so that came up, and excuse me, this is the landing page for each of our algorithms. So every algorithm that you host on this platform has a landing page like this: overview, title, description. I've actually added some keywords like blood cell. So you saw me search by a keyword earlier: white blood cell, blood smear, hematology. And then this is actually written in Python. And we have some metrics here for a number of calls and average call duration, some sample input and output. So I'll just run that, and it'll run this with this sample input. I'm going to run this again later with a different input and generate another file right on the fly. And then below here, you can actually call this algorithm from other applications. So if you've got an application that's uploading a blood cell scan after directly from the microscope, and then triggers this algorithm to read it, it executes it, and then does the inference, and then saves it back out into the output data set. So you can actually call this from a command prompt. You can call it from a Java app, PHP, Python, R, Rust, Scala. All of this is wrapped in or access to a wrapped API. And so here you can see this secured, and we actually do the versioning here. We have access keys as far with API keys, and so these are actually changeable, and you can assign different API keys to different consumers or different use cases, so you can track who's accessing what. And that's important for things like governance and auditing and things like that, HIPAA compliance. So you need to know who's accessing what, and make sure that the right people have the right access to what they need, and the people that don't. So additionally, we have a wiki page for each of these algorithms. And so basically, we provide you a template, and you populate this with the specifics to your algorithm. And then, so we have reporting on an algorithm level. Administrators can actually look at these on a global level for the platform, but this actually shows you who's accessing what. So here it shows that I'm the primary consumer of this, excuse me, of this algorithm. So every time you create a new a new build, or every time you update your code and you want to test that against, say, what's in production, we save a new build. I'll show you that here in a minute when we go into the source code a little bit. So you have a new build, you have a candidate that you want to compare to what's versioned here. So that right now we have version 1.1 listed in here. So if we had a new build, it would appear above this, and you can test that and then promote it if you need to, or if you want to. Here we list our versions. So this is 1.1.0, and I updated this yesterday to improve the output of where show you where it saved the files. This can actually be triggered by an event listener, which then would auto run this, say, when there's a file set up in file saved into the hosted repository or wherever you're storing it. And then going into settings here, we actually host the inference code, host your algorithm in a Git repository, but this also works with external Git repositories like Bitbucket and GitLab, GitHub. And then so you can treat this no matter which repository you've got it saved in, or type of repository you've got it saved in. You can treat this just like you would a GitLab or GitHub repository. So going down, so we've got some closed source, so I didn't want to expose the source code to everybody. You can if you want. The language, Python, using Python 3.9. This one has GPU support. So if you were actually initially running a CPU, you could, and you want to change it to a GPU node, you could do that just by simply changing the environment. So this has permissions to access the internet, and then this can do what we call pipelining, and that's what I mentioned before. We can have algorithms calling other algorithms, be it Python calling Python or Python calling Java. So basically, you can string up different parts of a utility into an ensemble, or what we call a pipeline of algorithms that accomplish what you're doing. So you can modularize your code into different steps. And then, so I want to go into the source code and just show you kind of briefly. I won't get too deep into this, but so we're importing all of our modules here, and then so as a result, we have dependencies based on what we're using in the code. So we actually roll up these dependencies. So you list them in here with the versions, save that. And then whenever you click build here, it's going to create a new container that's self-contained and ready to be hosted. So once you click build, you can actually test your code down here at the bottom, do a sample input, and then it'll actually execute. You can compare that to what's actually in production. So once that's done, if you want to publish it, you can click that, and you can do a major or a minor or revision. And then also enable what we call insights, which is actually a metrics pipeline that you can track both operational and inference metrics. So if you have a value in here, like in this case, we have white blood cells, red blood cells, and then a confidence level, you can pipe that into a Kafka broker and consume that with something like Datadog.
So 5-minute warning.
So I'm going to go into just a little bit of code here. So we're calling the client, the Algorithmia client, with the API key, and we've got some sample input here, and we will we go from there. So we set our weights file here that we've actually uploaded from Google Colab, and then we run the inference. So what I want to do here real quick is I'm going to go into data sources, and then go into this. I'm just going to grab a random one of these files. I'm going to copy the data path and then go back into the algorithm. I'm going to run it with a new file. So it's running that. So it's doing the inference right now. It's already done. So you can see where it saved this file. So I'm going to go into the hosted data repository, and it will have appeared here. So I'm going to actually go into this repository and then go into output and sort these. So this is one that was just created, and we just actually did this inference from a blank image, not a blank image, a freshly scanned image. So it's really that easy to deploy, operate, and then version, edit, and manage the stuff in production. So with that, I'm going to transition back to Diego and the presentation.
Unmute. Thank you, Trey, for the demo. So, one of the things to think about here is why does what are we actually doing? Oops, sorry. There you go. Next slide, please. So why does governance matter? 67% of organizations today will actually have to comply with multiple organizations. And this could be everything from regulatory to HIPAA compliance, as Trey mentioned. And auditability, governance, and security are really the #1 challenge that organizations are having today in the MLOps space. So what is the Data Robot MLOps platform? A single environment for continuous integration and deployment of machine learning. We support data scientists, ML engineers, application developers, and DevOps engineers all in one nice package. And we optimize performance costs relative to the business requirements so that you're actually seeing the value not only of speed, but a return on investment of your ML efforts. So bring models quickly into production so you can deliver value with the highest degree of enterprise-grade security and governance with continuous integration and accelerated deployment is the name of our game. And with that, we're going to wrap up and say thank you very much and open it up for a question. Thank you so much.
A big virtual round of applause for Diego and Trey. Thank you both so much. If you're watching this, stick around, do some networking, and we'll see you at the next one.